Okay, so I'd like to start off by thanking the organizers for the opportunity to speak. And I just really am very sorry that I wasn't able to attend in person. I hope you guys are having a very productive meeting with lots of interaction. So my message in a nutshell today, I'm going to be talking about the holographic duality between vector models in 3 dimensions and higher spin gravity on ADS4. For this particular example, I'm going to try to convince you that you can very explicitly construct the dual gravity theory by starting from the CFT. So there's going to be a holographic mapping which takes us from the degrees of freedom of the CFT to those of the higher spin gravity. And the basic idea behind this holographic map is we're going to reduce gravity to its physical and independent degrees of freedom. We're going to reduce the CFT to its independent degrees of freedom. And then we're actually going to be able to identify the degrees of freedom in CFT with those in the gravity. So we'll get a very explicit map, and we'll see how the gravity is reconstructed from the CFT. The whole talk today is going to be at large N. Once we've got the mapping, we'll be able to see that it reproduces many of the general expectations that we have of holography. In particular, I'll show you that we get a valid bulk reconstruction. I'll demonstrate subregion duality, and I will discuss how the holography of information is realized. So this is the plan of the talk. I'm going to start off just by quickly stating what is the vector model higher spin duality. Then I'll talk about the gauge fixing of the higher spin gravity. We'll then move on to the reduction of the vector model. And then the meat of the talk is when we discuss bilocal holography of the vector model, which is our reconstruction of the dual gravity. And then we'll discuss some tests of the holographic map and wrap up with some conclusions. So the duality that we're talking about here is a duality between Vasiliev's higher spin gravity in ADS4 and ON vector models. This is possibly one of the simplest non-trivial examples of ADS-CFT. In particular, we know that the spectrum of operators in the CFT is not renormalized at infinite n. So we know the complete set of anomalous dimensions, at least for the single trace primaries. So we know the spectrum of the single trace primaries very well. And that means we know the spectrum of fields in the dual gravity very well. So this makes it a particularly simple example to study. The non-trivial content of the duality, at least in perturbation theory, is in the agreement between correlation functions that are calculated in the bulk higher spin gravity theory and in the boundary vector model. And there's been a complete comparison of these correlators. Agreement has been demonstrated. So there's really a lot of evidence for this duality. The specific model that we'll consider is the free ON vector model. So it really is just n free scalar fields that are massless in 2+1 dimensions. The spectrum of the primaries, well, there's a scalar primary of dimension 1, and then there is a whole bunch of spinning primaries. These are conserved currents. There's an independent current for every even integer spin, so at every 2s for s integer, and the dimension of this operator is 2s plus 1. As usual, the spectrum of the single trace primaries tells us what is the field content of the dual gravitational theory. So the dual gravity will contain a bulk scalar and a gauge field for each conserved current. So I'm going to start by discussing the gauge fixed higher spin gravity, and in this case, we'll be able to fix the gauge completely. So I'm going to follow Metsayev and work in light cone gauge. My conventions for light cone coordinates are shown here. So I produce x plus and x minus out of x0 and x2. x1, which I will just call x, is a direction transverse to the light cone, and z is the holographic dimension of ADS4, the radial coordinate. The metric, the usual Poincaré metric, written in these coordinates is shown. My conventions is that capital letters will always refer to gravity coordinates, and I will always use little letters for CFT coordinates. The gauge that we are choosing sets any gauge field with one or more plus polarizations equal to 0. After you've chosen this gauge, so you've set these fields to 0, the equations of motion associated to these fields must be imposed as constraints. Those constraints must be solved. And it turns out that those constraints determine all components of the gauge field with one or more minus polarizations. So that after fixing the gauge and solving the gauge constraints, the only components of the gauge field that remain are components that have an X and a Z polarization. The gauge field that you've got is symmetric and it's traceless. So if you go ahead and check how many independent components are there are only 2 independent components. So at each spin 2s, there's a total of 2 components of the gauge field that remain after gauge fixing, solving the constraints, and reducing to independent components. In this gauge, after gauge fixing, the components of the gauge field satisfy a particularly simple equation of motion. The gauge field divided by Z just obeys something that looks like a Laplace equation. That's something we'll use later. Another thing I'm going to need is the action of conformal symmetry on these gauge field components. So we know what the ADS isometries are. We know the killing vectors. So the first thing that you would do is just take the Lie derivative in the direction of the killing vector. The trouble with doing that is that ADS isometries, if you perform an ADS transformation, in general, you'll be taken out of the gauge. So you need to supplement this transformation with a compensating gauge transformation that brings you back into the gauge. And then we want to express the action of the generators on the independent degrees of freedom that we have chosen. So after gauge fixing, we now have the ADS isometries supplemented by compensating gauge transformations, and we've solved to reduce it to just independent components. The independent components I will choose is the gauge field A with all X polarizations, or the components of the gauge field A with one Z and all remaining X polarizations. And what you get from this exercise is a set of transformations that is defined on these 2 physical and independent components of the gauge field. I'm going to find it convenient to repackage the fields that appear. So we've got the usual ADS4 coordinates, and the fields that we've got is a bulk scalar, and then gauge fields of every even integer spin. I'm going to use an alternative description where I introduce an extra coordinate theta. When I introduce theta, the metric doesn't change. So you shouldn't think of this as an extension of space-time. Theta is not geometrical. Theta is simply a bookkeeping device. And I now consider this field capital phi, which is a function of 5 coordinates, the 4 ADS coordinates plus theta, and my gauge field appear in the coefficients of a Fourier decomposition of phi. So I've managed to repackage all of the fields of the higher spin gravity into a single field at the price of using 1 extra coordinate. So this is a summary of the things I want you to keep in mind. The gauge field divided by Z obeys what looks like a simple Laplace equation. We've repackaged all of the fields of the high spin gravity by studying a single field depending on the ADS coordinates plus 1 extra coordinate theta. And finally, the action of the conformal group, which I've denoted with L subscript direct sum, is given by the action of the generators in the correct spin 2s and dimension 2s plus 1 representation on each of the gauge fields. So I've written direct sum here because you're actually using a different generator of the conformal group on each gauge field. So that's the completely gauged fixed gravity description. So now we'll discuss how do we reduce to independent components in the vector model. Now, the spinning currents in the vector model are symmetric, traceless, and conserved. And if you count how many symmetric tensors there are, and then how many symmetric traceless, and then how many symmetric traceless and conserved, you find at the end of the day, there's only 2 independent components. And this matches the 2 independent and physical components of the gauge field. But you really have to solve all 3 constraints. So you have to take into account the fact that the currents are symmetric, traceless, and in particular that they're conserved. Now, to take into account that they are symmetric and traceless is quite straightforward. If you've got a traceless tensor and you perform a conformal transformation, it remains traceless. So the traceless condition doesn't produce any change on the generator, and neither does the symmetric condition. However, you can use the conservation equation to eliminate one of the polarizations of your current. And if you do that, and you then perform a conformal transformation, the polarization that you've eliminated will be regenerated by conformal transformation. So you have to perform a non-trivial reduction to the degrees of freedom that you want to keep after you've solved the conservation equation. And I want to just describe in detail how you perform that reduction, because it's that solving the conservation equation that really is the meat of reducing to independent components. So our higher spin currents are conserved. That's the first equation that you see, and traceless, that's the second equation. What we're going to do, this is going to really make the description much simpler, is we're going to introduce a Fock space description, not because we've quantized anything, but just to deal with tensor indices. And the current will be represented as a vector inside Fock space. So a mu is a creation operator, a bar mu is an annihilation operator. They obey the usual algebra. And the Fock space vacuum is annihilated by a bar. My current, you just take J with all of its indices, contract them with creation operators, and act on the vacuum. In terms of this Fock space state, the conservation equation is just A bar on D annihilates the Fock space state, and the traceless condition is that A bar squared is equal to 0. The advantage of this language is that it's very easy now to solve these constraints in the Fock space description. So in particular, here is the solution. So this capital vector J is the conserved current, the state corresponding to conserved current that we just looked at. This vector, little I, only packages components of the current that either have minus polarizations or polarizations indexed by B, which is transverse to the light cone. So what I've done here, I've used the conservation equation to eliminate everything with a plus polarization, and I'm left only with minus polarizations and the directions transverse to the light cone. And the way that I get the plus polarizations back is through this exponential over here. It creates the plus polarizations from the minus and the B polarizations according to the conservation equation. This exponential, I call it P. The reduced symmetry generators are the conformal transformations acting on this vector I. So we know them acting on J. They're just given by some operator O. To obtain the reduced conformal transformations acting on I, it's easy to show these are given by P inverse OP. So these O tildes would be the reduced symmetry generators. So as an example, here are the Lorentz transformations. I've eliminated the plus polarization. Now, even if you eliminate the plus polarization, in general, the Lorentz transformations would bring back the plus polarization. The J tilde generators obtained, as I just described, you can see that they never bring back a plus polarization, and there's no D by dA pluses. So this is a reduced description where you now really have eliminated one of the polarizations from the current. And this is the reduction that you need to perform in the CFT. The way we'll be performing the reduction in the CFT is that we'll be working with bilocal variables. So a bilocal variable is given by contracting the basic scalar phi a with itself. The first field is defined at T1 and X1, the second one at T2 and X2, and you sum over A. If you use the OPE to work out what is the OPE between these two fields, you'll find it's a sum over all of the single trace primaries together with their descendants. Here I perform the OPE about the midpoint of X1 and X2. So the operator after OPE is located at X mu, and Y mu is the difference between the two space-time positions. One of the roles that Y mu has is that it packages the different polarizations of the current. So in particular, if I look at an equal x plus bilocal, where I've set the x plus coordinates equal in the two fields contracted to produce the bilocal, y plus is equal to 0. And that means that now the bilocal does not package any components of the current that have a plus polarization. So the bilocal has kicked out one of the polarizations. If you now go ahead and act with the Lorentz transformation on the field phi, we know exactly how Lorentz transformations act on phi. You just use the usual co-product. You can verify that from the scalar field transformation that you know for sigma, you generate the transformation of the current after you've reduced on the plus polarization. So the bilocal at equal times is performing the reduction that eliminates one of the polarizations using the current conservation equation. So that's how we'll be doing our reductions, by using equal time bilocals. Good. And with that background, I can now describe what we mean by bilocal holography for the vector model. So bilocal holography was proposed by Daseniewicz in a paper that is now about 20 years old. And the basic claim is that holography is accomplished by change to gauge invariant bilocal field variables in the CFT. In addition to that, you need to perform a change of space-time coordinates to give a bulk interpretation of the bilocal collective field theory. And that's exactly what I'm going to do in this section. I'm going to show you that starting from the CFT and carrying out these two steps, we will obtain a higher dimensional gravitational theory. So that in this way, the bilocal holography is a constructive approach towards demonstrating ADS-CFT. But before we do that, I would just like to motivate these two steps, because there is a very clear motivation for both steps. So why did we change to invariant bilocal variables? Well, in the original CFT, if you perform the loop expansion, the small parameter controlling the loop expansion is h bar. If you look in the dual gravity and you ask what is the small parameter controlling the loop expansion, it's 1 over n. So you want to perform a change of the degrees of freedom, a rearrangement of your degrees of freedom, so that you move from a loop expansion parameter, which is h bar, to a loop expansion parameter, which is 1 over n. And that's the need for the change to invariant variables. It performs this change of the loop counting parameter. This is an example of a very general method to perform this change to invariant variables, known as collective field theory. And that would be applicable, for example, to matrix models as well. A step just like this, where you would change to invariant variables, and it would once again change you from a loop expansion parameter h bar to a loop expansion parameter 1 over n. So that explains the need to change to gauge invariant bilocal fields. Why do we need the change of space-time coordinates? Well, the scalar field phi a itself of the CFT transforms in an irreducible representation of the conformal group. So the bilocal, which is a product of two scalar fields, is in a tensor product of representations. This tensor product is reducible, and this direct sum over here shows you what representations you get. This, of course, is just the spectrum of single trace primaries, or equivalently the spectrum of fields in the dual gravity. Each field in the highest spin gravity transforms in an irreducible representation of SO23, so that it's in this direct sum basis that you get your gravitational interpretation. Each of these factors in the direct sum is a field in the gravity. So the basis that you've got the CFT and this tensor product basis is the wrong basis to construct the interpretation of the gravity theory. You have a Clebsch-Gordon problem to solve. You want to go from this tensor product basis to a direct sum basis. And the claim is that the change of space-time coordinates that we'll perform exactly accomplishes the solution to this Clebsch-Gordon problem. Okay, so why does the change to invariant variables change you from a loop expansion parameter h bar to loop expansion parameter 1 over n? So I wanted to give you some feel for why that's true. So I'm going to start off by thinking in naught dimensions. This has got everything to do with the color combinatorics. So I'm going to reduce to naught dimensions. I'm going to integrate d phi a of some action e to the minus s of phi a. So if I want to solve this model, the only thing I need to do is perform these n integrals, but I'm taking the limit that n goes to infinity. So in general, that's going to be a very complicated problem. But things simplify immensely if the theory has an ON symmetry. If the theory has an ON symmetry, then because the phi a's are in the vector representation of ON, it means that S must be a function of the unique invariance, which is phi a phi a. Then we know that the integration over all of the directions which are orthogonal to sigma is essentially trivial. The action doesn't depend on those. So we can integrate over all of those n-1 directions, and they give us all essentially the same contribution thanks to the ON symmetry. So that means that your integrand, after integrating over all of these extra directions, gets a contribution from having done n-1, or you could call it n integrals. So you get an integrand that's nettly raised to the power of n. And we have one more integral to do, which is the integral over sigma. If we now do a saddle point approximation of this integral, we are going to naturally generate the 1 over n expansion. So I hope that gives you some insight into why it is that this change of variables generates the 1 over n expansion. We are going to use bilocals. In the CFT, as I said, I'll be using little letters. I'm again going to be using light cone coordinates. So this is my conventions for the light cone coordinates of the CFT. And I'll be using equal x plus bilocals. Because I'm using equal x plus bilocals, I've solved the current conservation condition, and I've reduced already to independent degrees of freedom in the CFT. And what you will notice is this field sigma is a function of x plus x1 minus x1, x2 minus x2. So we've got a single field, which is a function of 5 coordinates, which should remind you of the gravity description that we got after repackaging all of the fields. Now, this bilocal develops a large n expectation value sigma naught. Sigma naught is nothing but the large n 2-point function, so it's quite simple to compute. And then we can expand about this large n value with the fluctuation that I've denoted eta, with the coefficient 1 over root n. It is this fluctuation eta that we are going to identify with the higher spin fields. Okay. So now let's come to the change of space-time coordinates. So we start off with the bilocal, which transforms in this tensor product. And the action of any element of the conformal group will be the usual coproduct action. So act on the first field, leave the second alone, plus leave the first alone, act on the second. And that's the description that we get the CFT in. We would like to move from the tensor product to the direct sum representation. So we would like to have the representation that's valid for the gravity. So L direct sum on phi, we want to pick up the correct action of each of these generators on the 2 components of the gauge field that we have retained. So it's solving a Clebsch-Gordon problem. We want to go from the representation L tensor to the representation L direct sum. So just before I show you what change of coordinates accomplishes that, I want to just do one change of coordinates. The bilocal field in the CFT depends on x plus, x1 minus x1, x2 minus x2, so 5 coordinates. But there's a symmetry under shifting x minus. So I can do a Fourier transform on x1 minus and x2 minus. And in the process, I will trade x1 minus for p1 plus and x2 minus for p2 plus. In the bulk, I've again got a symmetry under doing x minus transformations. So I can do a Fourier transform on x minus and trade x minus for p plus. So now in the CFT, my 5 coordinates are x plus p1 plus x1, p1 plus x2. In the ADS4, my 5 coordinates are x plus p plus xz and theta, this bookkeeping parameter. Now, what you can check is, here is a change of coordinates that goes from the CFT coordinates to the ADS4 coordinates. And using this change of coordinates, it's very easy to check that the direct sum representation on phi is 2 pi p plus sine theta on the tensor product representation on eta. So this does indeed accomplish the solution to the Clebsch-Gordon problem that we wanted. So this is a summary of bilocal holography. We phrase the dynamics in terms of the bilocal sigma. There's a large n value of sigma, which is sigma naught, and a fluctuation, which is eta. There's a change of coordinates that we do, taking us from CFT coordinates to the coordinates of the ADS4. And then we've got an identification between the ADS4 fields, which is this field phi. It's 2 pi p plus sine theta times the fluctuation eta of the bilocal. This mapping, I should stress, has been determined so far entirely by the CFT. We've been using the symmetry of the CFT to write it down, and we didn't use in any way results from the gravity. We just know that this particular result that we've got here implements the symmetries of the gravity theory correctly. So it's been completely constructive, just starting from the CFT. Now, everything that I've said here is for the free ON vector model, which is for the UV fixed point. You might wonder about the IR fixed point, which is interacting. And if you want to read something about that, my colleague, Joao Rodrigues, has written 2 papers on that, so I would refer you to those 2. I'm going to stick to the UV fixed point. Now that we've got the map, I want to see what does this map reproduce about what we know about holography. Okay, so first of all, do we get a valid bulk reconstruction? So for a valid bulk reconstruction, we would like our bulk fields to obey the correct equations of motion with the correct boundary condition. So what I'm going to use is the equation of motion of the CFT, and that's the only thing I'm allowed to use. Well, the equation of motion of the CFT, after rewriting using our change of variables and working out the equation for eta, you get precisely this Laplace equation acting on phi. So we get the correct equation of motion for every single spinning bulk field. Now you might ask, do we get the correct boundary condition? Well, as usual, the boundary condition is set by the GKPW map, and it's set at z is equal to 0. If you want to work out how do the bulk fields, this phi, behave when z goes to 0, I've written down a very useful identity here that we use to do that. What sits inside the cos is related to theta from the map, and what sits on this side is actually the formula for the primary currents. So what you learn if you take z to 0 is that the s derivative with respect to x minus of phi s. Now phi s is the mode of our field phi multiplying the cos 2s theta. So that s derivative of this mode is reproducing for you the CFT current. So by taking the field to the boundary, we do indeed obtain the CFT current. But actually, this doesn't quite look like the GKPW dictionary. If you remember, GKPW is formulated in de Donde gauge. The residual symmetry of de Donde gauge allows you to require that the high spin fields are traceless and not just double traceless. Once you solve the equation of motion and you study how does the solution obey near z is equal to 0, we find that there's a non-normalizable solution B and a normalizable solution A. And the fall off in Z of the normalizable solution depends on how many of the polarizations of the field are along the Z direction. The piece of the field which is leading as Z goes to 0 is when you have no polarizations along the Z direction. So the GKPW dictionary then takes a look at the solution and identifies the CFT current with this coefficient A in the fall off of the higher spin bulk field. Now this looks different to what we found. We had derivatives of the bulk field. Here it's a local relation, just J is directly related to the value of the bulk field. And in addition, we had 1 over Z just because the gauge field was divided by Z inside phi. So there's a 1 over Z sitting on this side, on the the left-hand side of the equation, for any spin, whereas in the GKPW dictionary, the normalizable component was multiplied by z to the 1 plus 2s. So naively, it looks like we don't have the right boundary condition. But actually, this is too naive. This discrepancy was resolved by Minton and Polchinski. And the way to resolve this puzzle is that bilocal holography is formulated in light cone gauge, not de Donde gauge. So you should perform a gauge transformation. So h primed is equal to h minus the derivative of the gauge parameter. And the way you fix the gauge parameter is you say you want h prime to vanish if it has one or more plus polarizations. As soon as you've said that, you fix the gauge parameters, and then you can check what does the GKPW dictionary become in light cone gauge. So denoting the gauge fields in light cone gauge with a prime, in the end, you find that the 2s derivative of the gauge field divided by z is proportional to the CFT current. And that's precisely the boundary condition that we have found. So this is a proof that bilocal holography gives you a bulk reconstruction for every single field in the gravity theory. Now, another well-studied property of holography goes under the name of subregion duality. So the idea here is restrict yourself to a subregion of the CFT. So we're going to restrict ourselves to this red interval sitting over here. That means that when we study our bilocals, both feet of the bilocal will sit inside this red region. And then the question is, how much of the bulk can you reconstruct from bilocals which are restricted to this red region? And the claim is that you can reconstruct everything up to the Ryu-Takayanagi surface. So this is the claim of entanglement wedge reconstruction. Actually, in this case, we're studying MT-ADS4, so the quantum extremal surface is the same as the Ryu-Takayanagi surface, so I could easily have said here quantum extremal surface. But the claim is, what we expect is that we can reconstruct everything up to that surface. Okay. So to explore what bilocal holography says, remember there's two excitations sitting inside our bilocal. We're going to consider excitations described by wave packets. The first excitation in the bilocal will be in a wave packet that's tightly peaked around x1 and around p1 plus. And the second excitation in the bilocal will be tightly peaked around x2 and around p2 plus. And then just by looking at the dictionary between the CFT and the ADS4 coordinates, you can verify this equation written in black. What that means is, so I've drawn a picture over here. In this picture, the horizontal direction is x, the direction transverse to the light cone. So in particular, this horizontal direction is parallel to the boundary, and this horizontal line is at z is equal to 0. So this is the boundary where the CFT lives. The vertical direction is the holographic z direction. If our excitations are localized at x1 and x2, then this equation written in black on the slide tells us that the bulk excitation sits somewhere on this semicircle. To tell exactly where it sits, we have to specify this angle theta. Tangent of theta would be opposite over adjacent. The length of the opposite side is just z. The length of the adjacent side will just be x minus the midpoint of the bilocal. So the tan theta is just z over x minus x1 plus x2 over 2. And if you plug in from our map, what is the value of z and x, you learn that tan theta is just determined by p1 plus and p2 plus. And you can actually check that this tan theta, this theta is exactly the theta that was appearing in our mapping. It's exactly the same theta, the bookkeeping coordinate. So we can localize to any specific point on the semicircle by choosing P1 plus and P2 plus. So we've got a very explicit understanding of where the CFT excitations map into the bulk. So if we restrict ourselves to this red region, we can put feet of the bilocals as shown by these blue squares, and we can reconstruct everything on these blue semicircles, or there's a second bilocal that I've drawn there with another blue semicircle. And then what you can see is by choosing bilocals with both feet in this red region, we can reconstruct everything up to this black line. What is the interpretation of the black line? Well, the black line is actually a geodesic. So this surface defined by the black line over here is in fact an extremal surface. It is the Ryutake-Yanagi surface. So what we've reproduced here is precisely the statement of entanglement wedge reconstruction. So the last thing that I wanted to look at was the holography of information. So the holography of information is a relatively recent discovery, although it was hinted at in much older literature. And it challenges locality. So if you're in local quantum field theory, so here I've drawn a certain Cauchy slice, and you have two regions A and B, and these regions are space-like separated. If, for example, you were specifying an initial wave functional on this Cauchy slice, you can specify the value of the wave functional in A completely independently of what you specify in B. They're space-like separated, they have nothing to do with each other. If there was a laboratory in A and another laboratory in B, they would function completely independently. What the principle of holography of information says, so this is something that was proposed by Subrot Raju and his collaborators. The claim is that in a theory of quantum gravity, a copy of all of the information available on a Cauchy slice is also available near the boundary of the Cauchy slice. And the claim is that this redundancy is already visible in the low energy theory. So if you're going to perform a measurement at some point B, located deep in the space-time, whatever you would learn from that measurement is already encoded in this green region, which is an arbitrarily small neighborhood of the boundary. Another thing that this tells you, and this shows you how different things are to quantum field theory, if you consider some region R located deep in the bulk, and you were to change the values of the gravity fields inside this region R, you would necessarily change the values of fields inside this green band. So in a sense, this is a signal of some redundancy. The degrees of freedom that are sitting inside this region R are not independent of the degrees of freedom that are sitting in this green band in a neighborhood of the boundary. Okay, so what are we going to try to do now? Well, the principle of holography of information is pointing out an unusual localization of quantum information and quantum gravity. And this is only a property of a theory of quantum gravity. So if we look for signals of this in bilocal holography, it will be yet another indication that the collective field theory of the bilocal really is reproducing a theory of quantum gravity. So that's why we wanted to look at this. The idea is that ADS-CFT gives us a non-perturbative definition of quantum gravity on ADS-4. So let's take the principle of the holography of information as a statement about quantum gravity on ADS-4. Using bilocal holography, we'll turn it into a statement about the CFT. And then we can see if the statement in the CFT holds or if it can be proved. If it turns into a statement which is not correct, that seems to suggest that perhaps bilocal holography is wrong. So it's just a way to test bilocal holography and to test the holography of information. Is this a true statement? One thing I would like to just clear up before we continue, on a first reading, it might look like the holography of information is just a tautology. I mean, we are used to describing quantum gravity in the bulk of the ADS by degrees of freedom that live on the boundary, the degrees of freedom of the CFT. Well, that's not what the holography of information is saying. It claims that the gravitational degrees of freedom living at the boundary are enough to give a complete description of the gravitational theory. So this is a statement purely about gravity, and you would have a similar statement, for example, in an asymptotically flat space where you don't have holography, not yet. Okay. So to really see what the holography of information is saying in the CFT, it's useful to ask, where do the single trace primaries map to in the ADS-4 bulk? And I want to remind you that the holographic coordinate Z is some factor multiplied by x1 minus x2. where x1 is a location for the first field in the bilocal and x2 a location for the second field in the bilocal. Now, the scalar primary is given by contracting the two fields at the same space-time location. So it's given by setting x1 equal to x2. But if you set x1 equal to x2, that z is equal to 0. So the scalar primary lives at the boundary. What about the spinning primaries? Well, the formula for the spinning primary is it's a sum over derivatives, different number of derivatives on each field, and there's some coefficient which depends on the number of derivatives acting on each field. In order to express this in terms of the bilocals, you can separate the two fields by a small amount, perform the derivatives now with respect to the x1s or the x2s, and after you perform the derivatives, set the x1s equal to the x2s. To be able to do that, you only need to separate x1 and x2 by an arbitrarily small amount. So we can still require that the mod of x1 minus x2 is less than epsilon, and we can pick epsilon to be as small as we like. So our coordinate z is x1 minus x2 times this factor of the square root of p1, p2 plus over p1 plus plus p2 plus. Now, as a property of light cone kinematics, we know that p1 plus and p2 plus are both positive. In that case, it's very easy to check that this factor always lies between 0 and 1. So that if we restrict x1 minus x to be less than epsilon, that means that z itself is restricted to be less than epsilon. So the conclusion is that the complete set of single trace primaries after mapping to the dual gravity are supported in an arbitrarily small neighborhood of the boundary. That's where all of the single trace primaries map to. Okay. Now let's ask ourselves, what would an operator that's deep in the bulk of ADS4, what does that correspond to in the CFT? Well, if we want an operator deep in the bulk, we need to have a large value for z. Since this prefactor always lies between 0 and 1, operators that are located deep inside the bulk are necessarily bilocals where the two fields in the bilocals are well separated. So x1 and x2 must be, x1 minus x2 must be large. And that's the only way that you can get a field deep in the bulk. So now we know what are fields that are deep in the bulk, and we know where the single trace primary operators live. Holography of information predicts that bulk operators can be expressed as elements of the boundary algebra. We know that the single trace primaries are elements of the boundary algebra. So if we could argue that bilocals with the 2 points well separated can be expressed in terms of the single trace primaries, we would be done. We would show that any field arbitrarily deep in the ADS space can be expressed as an element of the boundary algebra. But of course, this is precisely what the OPE does. The OPE is a product of two separated fields, and it expresses it as a sum over the single trace primaries, which are all located in a small neighborhood of the boundary. So the question about the holography of information really becomes a question about whether the OPE converges or not. So the old folklore tells you that the OPE does converge with the radius convergence set closest to the nearest operator in whatever correlator you're studying. This was studied in detail in a paper by Papadopoulou, Richkov, Espin, and Rattazzi. That's more than 10 years old. And what they studied was just specific examples of the OPE and just checking how fast does it converge numerically. And in all of the cases that they studied, it converges exponentially fast. The specific rate that determines this exponential convergence depends on whether you perform the OPE at the midpoint of the two operators or closer to one of the operators or something like that, but it's always exponentially fast. These results were obtained in Euclidean space, but about 2.5 years ago, Chow did the analytic continuation very carefully from Euclidean space to Minkowski space, and he was able to argue that in Minkowski space, you also have an exponential convergence of the OPE. So we find that the holography of information maps into the OPE, and well, the OPE does converge. Okay, so I'd just like to have some discussion and mention some future directions. So first of all, using bilocal holography, so specifically collective field theory of the vector model, we have constructed a higher dimensional gravitational theory. We've done it just by using the CFT, nothing more than the CFT. We've checked that the resulting holographic map really provides a valid bulk reconstruction. We've shown that it's a very detailed example of entanglement wedge reconstruction, and that it exhibits the principle of the holography of information. I think this is a very convincing indication that bilocal holography really is constructing the quantum gravity, which is dual to the original conformal field theory. Now, of course, the natural question is to ask if this can be extended to matrix theories. If you could do something like n is equal to 4 or other matrix theories, that would be fascinating. So for matrix theories, much less is known, but in the case of a single matrix, in fact, the collective field theory can be worked out in complete detail. This has been done by Dasaniewicz. And what you derive from the matrix quantum mechanics is a string field theory that describes the C is equal to 1 string. So in this case, the collective field theory again gives you a construction of the dual gravitational theory. If you study a free massless matrix in 2+1 dimensions, the big difference between this and a vector model is that now there's a lot more invariance. So in the vector model, you only had phi A, phi A. For the free matrix, you can take the trace of m at x1 and m at x2, but you could also take the trace of m at x1, m at x2, m at x3. So to get a trilocal, there's quad locals and so on. So there's a much richer space of invariance. And then the challenge would be to work out what is the holographic mapping in these cases. Now, so that's work in progress that's being performed with Jaco van Zyl and Pratik Roy. And what I can tell you at this point, because you have more coordinates appearing in the trilocals, quad locals, and so on, you have more bookkeeping coordinates. 4 of the coordinates of the CFT go to reconstructing the ADS4, but you've got additional bookkeeping coordinates. And if you work out carefully the OPE, the number of families of primary operators that you find, so that the primary operators organize themselves into families, and the number of families that you find matches the number of extra bookkeeping coordinates. So this is already very convincing evidence that there's going to be a dictionary in this case, but we haven't yet written it down. That's work in progress. But I think that this is a positive indication that collective field theory will provide a constructive version of holography in the case of the matrix 2. And thanks for your attention.